Hello student, in last lecture we discussed union of two binomial heaps, and in this lecture we will discuss some more operations on binomial heap. The next operation on binomial heap is insertion of a node in an existing binomial heap. The following procedure insert node x into binomial heap H, assuming that x has been already allocated and key x has already been filled in. That means the node which you want to insert in the existing binomial heap, you have to create that node. That means all the structure should be fully prepared for that particular node x, such that first of all you make an empty binomial heap H dash, and you do in line number 1. Then the node which are going to be inserted is x, so parent of x is nil because it is a single node, child of x is again nil, sibling of x again nil, degree of x again 0 because it doesn't contain any children, or head h dash will point to this node x. Now till now we have two binomial heaps. H is the pre-existing binomial heap in which we want to insert our node, and H dash we created a new binomial heap with a single node x which we want to insert. Now the idea is very simple. Now we will unite these two binomial heaps together with the help of binomial heap union operation. So as you can see that this process is very simple, and let's talk about the complexity of this procedure. And the complexity is very simple. This is a constant time, first line constant time, because empty binomial heap can be created in a constant time. We have already discussed that. This is a constant time, constant time, constant time, constant time. So in this algorithm, binomial heap insert from line number 1 to line number 6 produce a constant time complexity, but line number 7 in which we are doing binomial heaps, and as we already know that binomial heap union produce the log n complexity. So overall time complexity of this algorithm would be log n. Okay. So this is the time complexity. Now next discuss one more operation, that is extraction of the node with the minimum key. The following procedure extract the node with the minimum key from the binomial heap H and returns a pointer to the extracted node. Okay, first of all find out the which one is the minimum key in the whole binomial heap, and after finding out that binomial heap, it will remove that particular node from the binomial heap. And the procedure is very simple. Binomial heap extract min will accept the existing binomial heap, then it will find the root x with the minimum key in the root list of H and remove x from the root list of H. In line number 1 we will process the whole root list of the existing binomial heap and find out the minimum key. After the finding of the minimum key, we will remove that particular node from the root list of H. Okay. Now in line number 2 we will create an empty binomial heap H dash. We will create an empty binomial heap H dash, and in line number 3 we will reverse the order of the linked list of x children. X, please let me remind you, x was the node which have already removed, and there because x was at the root list of the binomial heap, it may be possible that it contains several children. Okay, now what we have to do now, we have to reverse the linked list of those children and set head h. That means the new heap, empty heap we created in line number 2 to point to the head of the resisting list. Okay, so that new list will be pointed by the head h dash. Now again we will use the binomial heap union operation, which will unite the h which was the previously given binomial heap and h dash, we've created new binomial heap, and we will make a union of these two and then return x. Okay, now let's discuss how it happens. Now let's say this is the existing binomial heap in which we have to delete the minimum key. Okay, now in this root list 37, 10, 1, we have to find out the minimum key. Now first of all we do consider 37 as a minimum, then compare it with the 10. Now 10 is lesser than 37, now it is our minimum, and then move to the sibling of 10 and become compare it 1. Now 1 become the minimum key. Now when we move forward, the sibling of 1 is null, so that's why we cannot move further. That means 1 is the node which has the minimum key. Now what we have to do now? We have to remove this node. We have to remove this node 1. Now if we remove this node, the whole tree which is rooted at this node, that this tree would not be accessible from there. So the remaining binomial heap would be this. Okay, now what will happen to the children of node x1? 6, 16, 12, 25. Now we have what we have to do? We have to reverse these lists, that means 25 first, then 12, then 16 and 6, and make a new heap. Okay, we'll make a new heap h dash like this. This was the new h dash which contains the 25, 12, 16, 9 or 16, 6, sorry, and as you can see in the previous slide it was 25, 12, 16, 6. So with the help of these subtree we will create our new heap h dash. Now till now we have two heap h and h dash. Okay, now next step is simple. We will combine or union these two heaps h and h dash, and after combination of after making union of this is the final result. And the complexity of again this procedure is log n, because it is going this procedure is using binomial heap union operation, so that's why complexity is log n. And the first line, which is find the root x with the minimum key in the root list of h and remove x from the root list h. Here we have to find out minimum in the root list of h, and as we already know, the maximum length of that particular root list can be log n. So the complexity of this whole algorithm is going to be log n. So complexity is order of log n. That means in log n time you can extract a node which has the minimum key. Okay, now good. Now let's discuss one more interesting operations, decrease key. Decrease key means you want to change value of some node and you want to decrease of that value. But the problem is, when you try to decrease the value of a node, it may be possible the new value is lesser than its parent, so the mean heap property may violate. Now we have to take care of that, and this binomial heap decrease key algorithms deals in a beautiful manner. So let's discuss this. The following procedure decrease the key of a node x in the binomial heap h to a new value k. It signals an error if the k is greater than x current key, because as the procedure itself say, you are going to decrease the value of any node. So if by mistaken you want to try to increase the value of that particular node, it may show an error. Okay, so binomial heap decrease key is accept three arguments. First one is the heap s h, then the node x whose value you want to change, and k is the new value. So first of all, it compares value of new value with the existing key value. if new value is greater than key of x, then it shows an error, and the error name is new key is greater than current key. Otherwise, if it is equal or less than the value of the current key, it is assigned to the key of x, and for the time being that particular node x is denoted as y, and let's find the parent of y will become z. While z is not nil, that means when the parent of the y is nil and key of y is less than key of z. Let me remind you, key y is a temporary name of the node x whose value got decreased. So if the value of y, key of y is less than key of z, then we have to exchange value of y and z, because it is a violation of min heap property. So by the exchanging, we want to restore that heap property. Now if y and z have satellite fields, exchange them to satellite field means if that particular node or key is used to get some fields or get some file from the database, or it is related to some other information, that particular information, that particular data have to be exchanged to. Okay, now after that the z becomes the new y, and parent of y, new y, becomes the new z. Okay, now if you look at this example, as example say the value 26 is decreased to 7. Now first of all, algorithm compares the new value with the existing value. So 26 was a greater and 7, the new value, is lesser, so it changed. So 26 changed by 7. Now this is our y, and parent of y, that means 16, it is our z. Okay, now value of y is greater than, lesser than z, that means it is violating the min heap property. What min heap property says? It says that value of parent is always lesser than or equal to its children. So this is a clear violation. Here is a violation. So we will change the value, and 7 come here and 16 come here, and this will become our new y. Okay, now in the next figure, this is our new y, and parent of y will become the z. Again, value of y is lesser than z, that means value of this node is lesser than the value of its parent. So again we have to exchange these two. Okay, so 10 will come here and 7 will come here, and this will become our new y, as you can see it here. Okay, so 7 is our new y. Now again we will compare this value with its parent. So if this is y, parent of this becomes z, and value of y is greater than 6, so that means there is no violation of the heap property, min heap property. That means our procedure stops here. So what can be the worst thing in our case? The value may be changed at the leaf node here, and it move to the root node. And as you already know, the length or height of a binomial tree is log n. Okay, previously as you said, for bk height is k, and value of k is log n. Okay, so the time complexity of this operation is log n. Okay, so time complexity of this decrease operation is log n. Okay, now let's discuss our last operation. This is very easy, only 2-line operation, but basically it's reusing some other procedures. So we want to delete some key. It's easy to delete a node x key and satellite information from binomial heap H in log n time. Why it is so? Because if you want to delete some key, first of all you have to decrease its value. If you want to denote some or delete some node from the binomial heap, you have to decrease its value by the minus infinity. Minus infinity means very low value. If that value is very low, that means it is lesser than any value available in the binomial heap. That means that particular value or node will propagate to root node, or after coming to the root node we can use extract min operation. Okay, we can extract that particular node as we have done earlier. So this algorithm, binomial heap delete hx, h is the name of the heap, x is the node which you want to delete. In the first line, what it does, binomial heap decrease key hx in minus infinity. That means it will decrease the value of node x to very low. And after completion of this procedure, what will happen, that particular node x will be propagated to the root node. Okay, now this value is the minimum in the whole binomial heap. So next operation is binomial heap extract min h. What it does, it will remove the minimum key. We have already discussed it. So these two algorithms are already discussed. So, and this new algorithm, binomial heap delete hx, use only these two algorithms, and the complexity of these algorithms are log n. Okay, and this is again log n. So complexity of this algorithm is log n. Okay, so binomial heap delete procedure makes node x with the unique minimum key in the entire binomial heap by giving it a key of minus infinity. So complexity of this deletion operation is again log n.